Kings
All
11
right.
Punjab sir.
Yeah.
Ask who top for him. Huh?
Hello. I've started the recording. So let us get started while people join. Okay. I'll share the screen. All right. So let me review certain things which we did yesterday and then we'll move on. We have shown that the power developed by a single blade, which we have denoted by capital P subscript V as half m1 dot v1 square minus v2 square. So here capital P stands for power and B stands for blade or bucket or vane, whatever you call it. And m1 dot for a single blade is the mass product into the translating control volume. V1 is the velocity at the inlet. V2 is the velocity at one of the outlets. And as we have shown, since the bucket is symmetric, V2 equal to V3. Now, M1 naught is a positive quantity, the way we have defined it. V1 square and V2 square are also non-negative. Okay. So if you subtract a positive quantity from V1 square, of course the value will be less than half M1 dot V1 square. So we can find an upper bound or maximum value of the power developed by a single blade. So engineers are always interested in bounds. You may not know the exact value of a quantity, but if you can find estimates of what can be the maximum value or upper bound, or sometimes what can be the minimum value, then it's of interest. So obviously this cannot exceed half m1 dot v1 square because you're subtracting something. So if v2 happens to be 0, then you get the maximum power. Okay. So power developed by a single blade cannot exceed half m1 dot vj square. Now we have talked about the power developed by an actual blade, and we have shown that when you subtract v2 squared, you have m1 dot u times vj minus u into 1 plus cos beta. Now beta is a blade angle, so if you can have a case where beta is 0, cos beta will be 1. So 1 plus 1 will give you 2. And this is a quadratic function, quadratic in u. So for a given m1 dot, this will have a maximum when u is vj by 2. Then you'll have vj by 2 here, vj by 2 here, multiplied by 2 here. So 4 in the denominator, 2 in the numerator. So you'll get half m1 dot vj square. So you see that you will be able to get this estimate, theoretically of course, half m1 dot vj square under these conditions when the blade angle is 0 and the peripheral speed of the wheel is vj by 2. But as we have said before, we cannot in practice have beta equal to 0 because the water which is deflected backwards will then interfere with the incoming jet. But it should be close to 0 to make the efficiency as large as possible. Okay, now we have discussed the effect of blade friction by introducing an empirical factor, a dimensionless constant, which we call Cb, which we will call the blade friction. So C stands for coefficient or constant and B for blade. So the relative velocity at the two outlets, which are equal, we are taking to be slightly less than the inlet relative velocity. So if you neglect blade friction and assume the flow to be inviscid, since the flow is steady in the translating frame, you can apply Bernoulli's equation, but only in the translating frame. And that shows that W2 and W3 are both equal to W1. Now, this of course is not a rigorous analysis, just to get a better number, a better prediction. Here, just throwing in a constant. And as I said last time, this is not a very important part of the course. However, some of the dual degree students may appear in GATE in next February, and you may come up with see a question there which has a blade friction factor in mind. So you might wonder what it is. Okay, so I'm throwing in all the information that is available in all the books that are there on this subject. Okay. Now with this, we have a slightly modified expression for the blade. We have a factor CB in front of the cos beta, and you should always try to, just as we found upper bounds, you should also look at special cases. Does this reduce to the equation that we have derived before? Answer is, you put then CB equal to 1 and compare this with what we had before. Okay, if you put CB equal to 1, you get the same expression that we got before by assuming the viscous effects. Now, we were looking at the power developed by the wheel. So we noted that the volume flow rate of water issuing from the nozzle is the jet area, which we are calling A subscript J. So capital A stands for area, subscript J for jet, and V is the absolute velocity as seen by an observer on the ground. J subscript denotes the jet velocity. But the volume flow rate entering the translating control volume is Aj times the relative velocity, which is Bj minus U. So this is what we were calling Q1 flow. So I'm putting a superscript flow here because we also sometimes use Q for heat. At least in the other part of the course, we will be dealing with heat. And the subscript 1 is for the section 1 of the translating control volume, which was the inlet. So compare this and this, you see that Q1 flow is less than Q. But we have to note that the liquid that is, which in this case of course water, which is issuing from the jet, will strike more than one buckets. Okay, so there are many buckets around the periphery of the wheel. So it's common to assume that all of the liquid will strike one or other of the buckets. That is, the entire flow will be captured by the buckets. So if you have a Pelton wheel where the buckets keep entering the jet and capturing all the flow, then the total time average power delivered by the fluid to the, what you may call the wheel or the runner or the rotor of the Pelton turbine, which is mounted on the shaft, is given by an expression similar to what we have here. Only thing is, instead of Q1 flow, that is the volume flow rate entering one blade, you will substitute the total volume flow rate Q. So this gives you the total power by the runner, which includes the power developed by several blades simultaneously. And this is a kind of time average part, average over one cycle, let us say. Cycle means one revolution of the wheel. So then Q flow is a constant, although Q1 flow here depends on the translated speed of the control volume. Okay, so if I substitute Q flow here, then this is just Aj Vj, which is independent of U. So this is a quadratic in U, and as you can see, when U is 0, the power developed by the runner is 0, because in this case the wheel is not rotating. And if U is Vj, then the fluid is not striking the buckets, or just grazing the bucket. So again the power is 0. So as you have told me in the previous class, the maximum of this quadratic will occur when U is Vj by 2. That is when the wheel is rotating at an angular speed which is such that the translated speed at the periphery of the wheel is half of the jet velocity. And if you take this expression and substitute over here, you get the maximum power developed. So you will have Vj by 2 here and Vj minus Vj by 2 here. Now the power which is delivered by the fluid to the runner is also called hydraulic power. The fluid, of course, is, in this case, of course, a liquid, which is water. So that's why we call it hydraulic. So these are terms introduced by hydraulic engineers. So we may, in some authors may talk about the power developed by the runner or the rotor, some authors will talk about hydraulic power. They mean the same thing. So the hydraulic power is given by the same expression that we have written here. I have simply rewritten it here. Now, the energy that is arriving at the wheel is in the form of the kinetic energy of the water jet. So you can think of a power that is available at the exit of the nozzle, which is the mass flow rate of the water into the kinetic energy, half Vj squared. And this P jet you can recognize as the maximum power that can be developed. The power developed by the wheel cannot exceed this. So in place of m dot, I can write the density of water into the volume flow rate Q flow coming out of the nozzle into half Vj squared. The Vj half Vj squared is the specific kinetic energy of the water at the exit of the nozzle. So we are using this capital P symbol to denote power, and here I have written here subscript jet. So this is the power available or power associated with the jet of water which is coming out. And you can define a wheel efficiency, which is the ratio of the power, actual power developed by the runner, or the power transferred by the fluid to the runner, divided by the power of the associated with the water at the exit of the nozzle. So this, the way we have defined it, eta wheel cannot exceed 1. That is obvious. Now, if you take this expression 113, this equation, and look at this equation 112, and take the ratio, hydraulic power is the same as the power developed by the runner, then you get the wheel efficiency. So you see that rho times the Q flow will cancel out, and you will have this factor 1 plus Cv cos beta multiplied by this factor U times Vj minus U divided by half Vj squared. So the half goes to the numerator as 2, and if you divide by Vj squared, you can write it as U by Vj into 1 minus U by Vj. So the wheel efficiency, I have put a subscript. So we are using the symbol eta for efficiency, and I put a subscript wheel to denote this is the efficiency of energy conversion of the wheel. So the wheel is converting the energy of the water jet, the kinetic energy of the water jet, to kinetic energy of the rotor. Okay. So this depends on this empirical factor, which is roughly a constant. The blade angle is fixed for a given design, so that's another constant. But U by Vj can vary. Okay, Vj might be fixed for you. Depends on what is the velocity at the outlet of the jet, but the speed with which the wheel rotates will depend on the load on your turbine. Okay, because at steady state, the power developed by the wheel must be equal to the power which is required, the resisting torque. And this is a simple expression which tells you that the maximum efficiency will occur when U by Vj is half. So this is what you may call the best efficiency point or the optimum point of operation. So if I put U by Vj equal to half, then twice U by Vj here will give you 1, and 1 minus U by Vj will give you a half, 1 minus half. So we'll have half times 1 plus Cv cos beta. Now again, if you want to see what can be the maximum value, so this is the maximum wheel efficiency for a given blade. So suppose beta is 0, then cos beta will be 1. If the fluid is really invested, Cv will be 1. Then 1 plus 1 by 2 will be 2 by 2, which is 1. Okay. But of course, in reality, you cannot make beta equal to 0, and there will be some friction. So this value will be less than 1 in practice. But whatever it is, the way we have defined it cannot exceed 1. Now we'll introduce a term which is called the gross head. So look at the schematic of the Pelton turbine. This is the turbine here. and the upstream reservoir is called the head race. So this is what you may call headwater. So this could be at the top of a mountain or hill. So you have air above, and this is the level of water in the upstream reservoir or headrace. And this inverted triangle and these three small lines indicate that the pressure here is atmospheric pressure. Now, the downstream reservoir into which the spent water falls is called the tail race, and this is called tailwater. So the water will flow through a shallow tunnel which is slightly inclined. You may call it the pressure pipe or the pressure tunnel. And then it will fall almost vertically through a pipe of large diameter called the penstock. And then it will go through this nozzle, and the nozzle will direct a jet of water onto the buckets. Now we want to find what is the velocity of the jet at this point. So when the jet of water comes out, again, all around the jet you will have air. So we can apply Bernoulli's equation between this point, which I've called 1, at the interface between the water and the air of the upstream reservoir, and a point 2 at the exit of the nozzle. Okay. And this height difference between the center line of the nozzle and the level of water in the upstream reservoir headrace is what we are calling H subscript 1 or H subscript GR. GR for gross. So this is the gross head. So we can define the gross head this way. It is just H1, which is the elevation of the level of water in the upstream reservoir or headrace above the center line of the nozzle from which the jet of liquid is coming out. Now, as the fluid moves through the pressure tunnel or pressure pipe and the penstock to the base of the nozzle, okay, the base of the nozzle is here, somewhere here, okay, that is the exit of the pipe connecting to the penstock. There will be a frictional head loss due to viscous effects, which I am calling H subscript loss. Okay, so by H subscript loss, I denote the head loss between section 1 here and not section 2, but the inlet to the nozzle. The nozzle is considered part of the turbine, and you have to design the nozzle to get good efficiency of the entire system. So we are considering separately this pipeline, etc. Okay. So if there's a head loss, then the head that is available here at the inlet of the nozzle will be less than this gross head by this amount, which is the head loss. So this is one advantage of talking about heads. Okay. So look at a total head, which is the gross head. And from that, if you subtract the head loss, so that is H1 minus H loss, that is the head that is available at the entrance to the nozzle. And associated with that, you can talk about a power available at the base of the nozzle, which will be simply m dot GH or rho times Q flow GH. So P available, P, again capital P is used for power, and this subscript AVAIL is for the available power. This is the power available not at the exit of the nozzle, but at the inlet of the nozzle. Okay. And some people talk about efficiency of the pipeline, which is the ratio of this available head to the gross head. And again, the way it has been defined, this will be less or equal to 1. So one way, if somebody in a problem gives you the transmission efficiency, then the available head will be the gross head times this efficiency, the transmission efficiency. And this H gross you can find by looking either at the figure or the value might be given to you. So that is from the geometry of the system. Okay. So look at the center line of the nozzle. Think of this as one horizontal level. And look, so we are calling, say, y equal to y2 or z equal to z2, whatever it is. And z equal to z1 or y equal to y1 here is the level of water in the upstream reservoir. So this level difference is the gross head. From that, if you subtract the head loss, you get H, or multiply H by the efficiency, if that is given. So this H will be less or equal to the gross height. And this in turn is less or equal to the, this is less or equal to the gross head. If the head loss is 0, that is if you idealize everything, then it will be equal to H1. Okay. Now we want to find the nozzle velocity, jet velocity at the nozzle exit. So we'll apply what you may call the extended Bernoulli equation along a streamline which I have already indicated. So look at this blue curve here. It's a schematic of a streamline. So a fluid particle here will start to flow down along this, and it will go out through 2. So you can apply the extended Bernoulli equation between point 1 and point 2. So the extended Bernoulli equation includes the head loss. So it will be the total energy at the upstream point 1, which will be equal to the total energy at the upstream point, downstream point 2 plus the head loss. So head loss will be positive, so the total energy or total mechanical energy at the downstream point or downstream section will be less than the total mechanical energy at the upstream section by this amount head loss. And if the fluid is truly inviscid, then this H loss will be 0. Okay. So here, of course, what we have done is I've just accounted for the head loss between point 1 and the base of the nozzle. Okay. And I've neglected the head loss inside the nozzle because I'll account for it later. That is the convention. As I said, the nozzle is considered, the design of the nozzle is considered a part of the design of the turbine system. Okay. So here I have assumed for the time being that the viscous losses inside the nozzle is negligible. And 2 is a section at the exit of the nozzle, but 1 is not the inlet of the nozzle, it is the upstream point of the head race. So we have to include the head loss in the pipeline, which includes the pressure pipe as well as the penstock. Now, the pressure at section 1 obviously is atmospheric pressure. At section 2, which is the exit of the nozzle, the jet of water is surrounded by air all around. So there also the pressure is P2 is 2 atmosphere. So the first term on the left hand side and the first term on the right hand side of equation 122 will cancel out. Now, what is V1? It will be the flow rate by the area at section 1, which is the area of the upstream reservoir. Now this of course is a schematic. I've shown it like a tank. This is a very large reservoir. So the area will be large, so the velocity here is negligible. So the rate at which this level will go down is extremely small. And the rate at which this level goes down is the velocity of the fluid particle at the surface, free surface. And half times V1 square will be the kinetic energy. So that can be neglected. So if you go back and look at this same equation, the first terms are cancelled out on each side. The second term on the left hand side can be neglected. And Y1 is Y2 plus the gross height, H1. Okay. So if you go back to this figure, Y1 minus Y2 is H1 or the gross head. It is the level difference between the level of water in the upstream reservoir and the level of water at the center line of the nozzle. So this equation simply reduces to H1 equal to V2 square by 2G plus the head loss. So left hand side is actually the potential energy. This is the kinetic energy and this is the head loss. So V2 square by 2G then is H1 minus H loss, which we have defined as H, the available head. So you can see why this definition is useful. H1 was a gross head, okay, which you can find from the geometry of the figure. And from that, if you subtract the head loss in the pipeline, then you get the available head, which is V2 square by 2G, where V2 is the jet velocity at section 2. That is at this section. Okay, so V2 is Vj. So assuming that the flow inside the nozzle is inviscid, you have a simple estimate here. V2 is square root of 2gh. Okay, And if you assume that that flow inside the pipeline is invisible, then it is simply 2G times H1. But there will be some head loss, so H will be slightly less than H1, which is the level difference. So the ideal jet velocity at the exit of the nozzle is, I call it Vj, Vjet here. Sometimes I'm calling Vj also for brevity. I put a parenthesis here and another subscript which I'm calling ideal. That is assuming that the fluid flow inside the nozzle is that of an ideal fluid. You have this estimate root of 2gh. So this is when the frictional losses in the nozzle are negligible. And h is the head which is available at the base of the nozzle, not at the exit of the nozzle. Now, there will be in practice viscous losses in the nozzle, so the actual velocity will be slightly less than the ideal velocity. So it's customary to define a coefficient of velocity or velocity coefficient for the nozzle. I've given it the symbol which is used by most authors, C, capital C or uppercase C with a subscript V. So this V is for velocity and C is for coefficient. So this is a non-dimensional constant. Now don't confuse this with heat capacity at constant volume. We are not dealing with that over here. Okay. So Cv for the nozzle is defined as the actual jet velocity by the ideal jet velocity. So therefore the jet velocity, actual jet velocity of the nozzle. So to emphasize it, I've used the symbol equal to sign with the dot on top, means Vjet is defined as the actual jet velocity. Okay. So henceforth I will not use the term actual, subscript actual, but here to emphasize it, I've done it. Okay. So the jet velocity is Cv times the ideal jet velocity. Okay, which is square root of 2gh. And as you can see, the way this has been defined, Cv will be less or equal to 1. And typical values lie between 0.92 and some authors say 0.98, some say 0.99. If you can have a well-designed nozzle, then the Cv can be up to 9.99. So the losses inside the nozzle are between 8% and 1%. Okay, if there's an 8% loss, then Cv will be 0.92. Now one can define a nozzle efficiency, which I'm calling eta subscript nozzle. It is a ratio of the energy at the outlet of the jet to the energy that is available at the inlet to the nozzle. Okay, so the energy available at the nozzle outlet is in the form of the kinetic energy of the jet. So that is the capital P with the subscript jet, which is half m dot into Vjet square. And you can divide it by the available power, which is m dot gh. Okay, so it is Vj whole square by 2gh. So one can write it as this quantity in parenthesis whole square, Vj by square root of 2gh. And you recognize this term in the parenthesis as Cv. So the efficiency of the nozzle turns out to be simply the square of the velocity coefficient. Now we'll define a quantity which is called the hydraulic efficiency, which is the ratio of the power delivered to the runner by the fluid to the available power. So available power means the power that is available at the base of the nozzle. Okay. So eta with the subscript hydraulic is the efficiency of conversion of energy from whatever is available at the base of the nozzle to the rotor. So you can either call it the power developed by the runner divided by now what you can do is multiply and divide by Pjet. Then you can write it in a form where you can relate, which will help you relate the hydraulic efficiency to the efficiency of the nozzle and the efficiency of conversion. Okay. So if we compare equation number 135 with equation number 134, you see the P jet here and the P jet here will cancel out, and you get back P runner by P available. This is the P runner and this is the P available. But the reason we have written it this way is that you'll see that this ratio P jet by P available, the power available at the exit of the nozzle to the power available at the base of the nozzle, is the efficiency of the nozzle. And this we have defined as the efficiency of energy conversion by the wheel. Okay. So wheel is getting energy in the form of kinetic energy of the jet, but all of it cannot be converted to kinetic energy of the rotor. So this ratio we have defined as eta wheel. So you can see that eta hydraulic is the eta nozzle into eta wheel. So we are not looking at the efficiency of the pipeline transmission because that is not part of the turbine design. Okay. Now eta wheel, we have found a simple expression for it before. Okay. If you go back, and today I'll upload this in MS Teams, we have shown that eta wheel is of this form. Okay. So this, of course, is the prediction assuming inviscid flow and many other assumptions, and then throwing in a empirical factor to account for viscous losses. Take this expression for eta wheel and multiply it by eta nozzle, which we have shown is CV squared. So we'll have CV square multiplied with this quantity. Now CV square I can write as 1 CV into another CV. So for convenience, to get it in a neat form, I've written this expression as, I've kept the 2 outside and 1 CV inside, CV into E by Vj, and the other CV I have moved inside this parenthesis and written it as CV minus CV times U by Vj. And this factor outside I've left as it is. Now you see that CV into U by Vj is appearing outside as well as inside. So let us see what this quantity is. By definition, the velocity coefficient of the nozzle is the actual jet velocity by square root of 2gh. And if you multiply it by U by Vj, then you see the Vj in the numerator and the Vj in the denominator cancels out, and you get U by square root of 2gh. So U is the peripheral velocity of the wheel, the translatory velocity at a point at the periphery of the wheel. So this is sometimes called the speed ratio, or a better term is peripheral velocity factor, which is U, not U by Vj, but U by root of 2gh. Okay. So CV times U by Vj you can recognize as phi, which is U by root of 2gh. So if we take this expression on for this quantity CV multiplied by U by Vj, given by equation 140, substitute into this equation. Then here you get twice phi into CV minus phi into 1 plus CV cos beta. And once again, CV is the empirical factor which is very close to 1. CV is the blade friction factor. And this CV, I have not used lowercase c, then you may think it's specific heat capacity at constant volume, which you might be using in other courses. And capital CV, well, it could also stand for heat capacity, but not specific heat capacity. So this symbol is not used very frequently. Okay. So this is the coefficient of velocity, or velocity coefficient for the nozzle, which again is close to 1. Okay. And beta is the blade angle at the exit. Since the bucket is symmetric as assumed, the blade angles at both the exits are the same. So I'm not writing beta 2 or beta 3, simply beta. So from this simple prediction, you see the hydraulic efficiency is 0 when phi is 0. That is when U is 0. Okay. And again, when U is square root of 2gh, okay, that is, sorry, not U equal to square root of 2gh, U phi equal to CV. Okay. So this means that U equal to Vj, or U by square root of 2gh is equal to CV. Again, eta hydraulic is 0. Now, this is a quadratic in phi. So you tell me when for what value of phi will you get the maximum efficiency here?
CV by 2.
Yeah.
C by 2. C by 2.
Okay. So here I have not given the value. Okay, it's easy to find. It is CV by 2, which will be less or equal to half. Okay. Because CV maximum value can be 1. Okay. So if I take that value phi equal to CV by 2 here, then twice phi will be CV. And CV minus CV by 2 will be another CV by 2. So you'll have CV squared and a half here into 1 plus CV cos beta. And again, let us look at bounds. If suppose beta is 0, then cos beta is 1. In any case, cos beta cannot exceed 1. CV cannot exceed 1. Okay. So if this is 1, that is if the fluid is ideal. If the fluid is ideal, CV will also be equal to 1. Then you have 1 plus 1 by 2. So the way we have defined it, the maximum value could be 1, but not more than 1. Of course, this 1 will not be achieved in practice because of viscous effects. Now, another term that you may come across is head developed by the turbine. So as we have seen in the module on the first law, we had an expression that the power developed by a rotor or runner is the mass flow rate into G into the head, which is the difference of the heads at the inlet and outlet minus the head loss. So H turbine is H at the inlet of the control volume minus H at the outlet of one of the two outlets which are the same. Okay. Minus the head loss. Okay. So if you have the head developed by the turbine, you want to find the power developed by the runner, simply multiplied by rho Q G. Okay. So this is a very simple expression that we may be using again and again by solving problems for this course. Okay. So head developed by the turbine, if I call it H with a subscript turbine, okay, or sometimes I will simply call it HT. If you have the head developed by the turbine, you can find the power developed by the runner. Or conversely, if the power developed by the runner is given and the flow rate is given, you can find what is the head. Okay. Now I can take this and substitute into the efficiency expression for efficiency here. The available power is m dot gh, and the power developed by the runner is m dot g times h turbine. So you see that the hydraulic efficiency is the head developed by the turbine by head. So the utility of this expression is that given the head available at the base of the nozzle, if you know what is the hydraulic efficiency, then you can get what is the head developed by the turbine. And once you have the head developed by the turbine, you can find the power developed by the runner. Okay. Now, the power that is developed by the runner is not going to be equal to the power delivered to the output shaft of the Pelton turbine. So the Pelton wheel will be mounted on a shaft, and on the same shaft you will have a alternating current generator, electric generator. So that will generate electricity. So as a mechanical engineer, you will be interested in what is the power that is delivered to the coupling of the output shaft. So this coupling will couple the output shaft of the turbine to the input shaft of the electric generator. And from then onwards, it's the job of an electrical engineer to get an efficient generator. Okay. So due to some losses in the bearings, the power which is delivered by the fluid to the runner will be more than the power that is actually delivered here. Or in other words, the power that is actually delivered to the coupling of the output shaft will be less, slightly less than the power that is delivered by the fluid to the runner. And the power that is delivered by the fluid to the runner is the hydraulic power. So this is due to mechanical losses in the bearings. So one can define a mechanical efficiency. I'm calling it eta with a subscript MECH for mechanical. is the ratio of the power which I'm calling P, which is delivered to the coupling of the output shaft to the power delivered by the fluid to the runner or the hydraulic power. So the actual power that is given to the electric generator, the shaft at the input to the electric generator is eta mech into P runner. So sometimes we may use eta m for brevity, but here I've written eta mech. So eta mech is P hydraulic. Sorry, eta mech times P hydraulic will give you the power that is delivered to the coupling of the output shaft. Now what you can do is find an overall efficiency, which is the power delivered to the coupling divided by the available power. So this the available power means the power which is available at the base of the nozzle, because the nozzle is part of the turbine system. So we want to know how much of the power that was available at the base of the nozzle is actually converted to power at the output shaft of the turbine. And once again, I can multiply and divide the right hand side of this equation by P runner. So P runner in the numerator of equation 151 and P runner in the denominator will cancel out, and you'll get back P in the numerator here as in this equation, and P available in the denominator here as in here equation. Okay. Now once again, we are doing this to relate eta overall to eta mechanical and eta hydraulic. So we'll recognize the first term as eta mechanical and the second term as eta hydraulic. So the overall efficiency is the product of the mechanical efficiency and the hydraulic efficiency. And hydraulic efficiency we have seen is the product of the wheel efficiency and the nozzle efficiency. So the overall efficiency one can write as the product of these three efficiencies or as the product of these two efficiencies. So when solving problems, sometimes values of these efficiencies will be given, and then you may be required to find eta overall. Once you have eta overall, then you can get the power delivered as eta overall multiplied by rho Qg times the head which is available at the base of the nozzle, which is again the gross head minus the head loss in the pipeline. Now we have defined so many efficiencies. So I've given you a ready checklist here where I've given you a summary of the definitions of all the efficiencies. So at a glance you can see. So let me go through it again. If you want to find eta mechanical multiplied by the power delivered by the fluid to the runner. Again, the power delivered by the fluid to the runner is eta wheel multiplied by the power of the jet. And the power of the jet is the available power multiplied by the nozzle efficiency. And if one wishes, I can define a hydraulic efficiency, which is the power delivered by the runner by the available power. And the overall efficiency is P by P available. So here, of course, I have not written the pipeline efficiency. I've just written the terms relating to the turbine system here. So are there any queries regarding this part? Well, if not, then I'll stop sharing this and open another document. All right, now I've said this before, we are interested in energy conversion. So as you can see, what we are doing is we are converting the potential energy of water at the top of a hill or mountain to kinetic energy of the water jet. And by allowing the jet to strike the buckets and allowing the wheel to rotate, we are converting the kinetic energy of the water jet to kinetic energy of the wheel or shaft. And ultimately that will be used to drive what you may call an alternator or an AC electric generator to generate electricity. So ultimately the mechanical energy of the rotor will be converted to electrical energy. So we need to know what will be the frequency of the alternating current that is generated. Now unfortunately you don't have a course on electrical machines. Okay. As you are aware, the curriculum in IITs gets revised from time to time. New courses come and then some old courses have to be deleted. Okay. So when I was a BTech student, we used to have a course on electrical machines in our second year, second semester or fourth semester. The course is to be offered by our electrical engineering department. Unfortunately, that course is no longer offered to mechanical engineering students. Okay. But it is of interest to mechanical engineers also because ultimately, as you can see, when you are generating power, you'll be using it to generate electricity. So I'll just give you the result here, which you may find in any book on electrical machines. So the frequency of the line frequency, okay, is determined by the number of magnetic poles in the generator and the rotational speed of the rotor of the shaft. So that is sometimes called synchronous speed. So if capital N is the synchronous speed in RPM, okay, that is revolutions per minute, then you have an expression 120 into the frequency of the alternating current. So I've called it F with the subscript AC. The reason I'm putting this subscript is that similar symbols may be used to denote other quantities. Okay, so to avoid confusion, I have written F with the subscript AC for the frequency of the alternating current which is generated by the alternator. So if this is in hertz, which is 1 by seconds, and if small n with the subscript poles is the number of poles, then the synchronous speed is 120 into F by n number of poles. So this is the line frequency which you want to generate, and this is determined by your construction of your alternator. Now in this expression, of course, I've taken the number of poles, which has to be an even integer, so it is twice the number of pole pairs. So you may come across a book where you will have a formula 60F by n, but in that case you would interpret n as not as the number of poles but as the number of pole pairs. So here most authors of textbooks on electrical machines will use this kind of a expression where they use the number of poles which is twice the number of pole pairs. Now, as you know, in our country, the frequency is 50 hertz. And you don't want to change it because then electrical appliances, electronic appliances, they'll all get damaged. Okay. So if you want to maintain this frequency at 50 hertz, then what will be the rotor speed? And this must be the same as the speed of the Pelton turbine, shaft of the Pelton turbine. So you have to design a system as a mechanical engineer where the Pelton turbine shaft rotates at a constant frequency. Because if n varies, then the line frequency will change, and that will lead to disaster. Now, of course, this n, just giving you some numbers, minimum value is 2, so I've gone up to 12. Okay. So if I multiply it by 50, it is 6,000 divided by the number of pores in RPM. Okay. So if n is 2, then this will be, your shaft must rotate at 3,000 RPM. If you have an electric generator with 4 poles, then it must run at 1500 RPM. If it has 6 poles or 3 pole pairs, then your turbine must run at 1000 RPMs. If there are 8 pairs, then it should run at 750 RPM. If there are 10 poles or 5 pairs. If there are 6 pairs or 12 poles, then it will run at 500 RPM. Okay. So you see that the speeds at which you want to run the turbine will be something like 3000 or 1500 or 1000 or 750 or 600 or 500 and so on. Of course, again, there will be a slip which electrical engineers talk about, and the actual end might be slightly different. Okay, but this is a theoretical estimate. So important thing that you understand is that as a mechanical engineer, you have to devise a turbine which must run at constant rotational speed, because number of poles for a given generator is fixed, and you want a line frequency which is always 50 hertz. Okay, so you have to put a governor and have some way of governing the speed of the belt and wheel or some other turbine. So what should be the rotational speed of a hydraulic turbine? So as I said before, a hydraulic turbine is used to drive an electrical generator mounted on the same shaft. And if I say FSC is the frequency of the electrical output, this must be kept constant. So in our country, it is 50 hertz. If you go to the US, it will be 60 hertz. Now you might be referring to some books on fluid mechanics written by American authors. And all of them, if it's an undergraduate textbook, will have a chapter on fluid machinery, and there'll be problems. So you may see that they're using 60 hertz, or if you calculate the line frequency, you may be surprised to find it's not 50 hertz. Okay. But in their country, they keep it at 60 hertz. And as I said before, for a given generator, the number of poles is a constant, an even integer. So therefore, the rotational speed of the turbine must be constant. So n is in RPM. If you want the angular speed, which I am denoting by capital omega in radians per second, then you multiply it by 2 pi by 60. So capital N by 60 is the RPS, the revolutions per second. Multiplied by 2 pi, you get it in radians per second. And we have done our analysis by assuming that the radius of curvature of the wheel was large. So we replaced the rotary motion by a translatory motion. That is why we could assume that the frame of reference which was translating was an inertial frame. So we are dealing with the peripheral speed of the wheel or velocity of translation at a point on the periphery of the wheel, or it could also be at the pitch circle, which is very close to the periphery. So this capital U, which was the speed of translation of the control volume that we used in analysis, will be the pitch circle radius multiplied by omega. Or if the pitch circle is not given in the problem, if the diameter of the wheel is given, it is simply d by 2, diameter of the wheel by 2. So this must be kept constant. Okay. So whatever you do, you have to ensure that omega or equivalently u must be kept constant. Okay. And for that, you need to look at what is called governing of the Pelton turbine. Okay. It is almost 12 o'clock, so I will not go further. I've given you an idea of what is meant by governing. You want to keep the angular speed constant. And how it is done, I'll discuss tomorrow. Excuse me. Are there any queries? Okay, I am stopping the recording.